So 1 more minute. Maybe I'll just get started. All right, welcome everybody. This is a San Francisco Big Analytics. So today we have an event talking about the federated learning. Before we do that, we want to quickly just remind you there's other events we scheduled for next week, next Tuesday actually, talking about deep learning based recommender systems. The speaker is until recently he's the head of the AI lab in the company based in China. It was the called Crosssite. That is the second largest short video company in China. Basically, the first one is ByteDance, producer TikTok. So this is the second largest video company, short video company in China. So he's going to talk about their recommender systems. But today we have Holger from NVIDIA talk about federated learning. So let me just get to that page. Let me stop sharing. Actually, you can share your screen. Okay, let me see. Okay. So yeah, we want to first we want to thank the AI Camps to provide the Zoom for us. So AI Camp is a partner who provide a free Zoom for our community. So we want to thank you for providing that. So this is kind of a new federated learning is a new area. So we're quite excited about today. We can have Dr. Holger Roos from NVIDIA to discuss the Flare, who's the runtime engine, runtime environment for the federated learning. So Dr. Roos is working on this for a while. He's a senior applied research scientist at NVIDIA, especially focusing on deep learning for medical imaging. So he has a lot of words, and he's also an associate editor for IEEE transaction for medical imaging. So so with that, go to Dr. Roos. Dr.
Thank you very much for the kind introduction. And yeah, as Chester said, I'm an applied research scientist at NVIDIA, focusing on federated learning for the last couple of years now. And today I wanted to introduce our SDK, or our open source solution to do federated learning in the real world. We called it a NVflare, so NVIDIA Federated Learning Application Runtime Environment. And it's really the idea that it can be a tool that you can use to bring your, to distribute your machine learning or data science pipelines to allow you to do collaborative learning across multiple institutions. Maybe I'll start with a little bit of a background. Especially, so my background is in healthcare, and that's also where we started a federated learning effort in NVIDIA, mainly on the medical imaging side. But NVflare is actually more general than that, so we can talk about that later. But in medical imaging and healthcare applications specifically, we have this problem that it's very expensive and difficult to train robust and generalizable AI models. So starting from the data preparation, you typically need expert knowledge in order to annotate images for certain disease categories, or even healthy anatomy in the image is very difficult to define for non-experts, right? So we cannot do crowdsourcing or approaches like that to annotate our data. So it's one of the challenges. Then data diversity is important, right? In order to build models that can actually generalize to different patient populations, different acquisition protocols, different scanner types, in order to be robust and generalizable. Typically, the model needs to also see examples of those kind of data. And of course, we have this data privacy issue, or data privacy is very paramount in healthcare. Like, we want to make sure that no patient identifiable information is being leaked through the AI training process or with AI model releases and things like that. So all of these challenges also highlight the need for collaboration, right? In order to build more larger data sets, to get more experts involved to annotate data and things like that, you need to have multiple institutions involved in building data sets and collaborating on building AI models. At the same time, to measure robustness of these models, you need to do multi-institutional evaluation of the models, which has been not done very often so far in healthcare. So this is like one of the growing needs to actually have good infrastructure to allow us to evaluate models on multiple sites. So on the left side, you see some stats saying that only 6% of published model articles or AI models in healthcare have been even evaluated on multiple institutional data. So the federated learning paradigm, just to explain what that is that you can actually do the AI model development and evaluation across different institutes, right? So each hospital can keep control of their data, but they share some sort of knowledge in form of model updates or partial model states with each other in order to train more powerful AI models in a collaborative fashion. And of course, this is a form of decentralized model training. We have the evidence that this is actually working in the real world. There have been several real world studies using federated learning for healthcare applications. So we have pancreatic cancer detection, for example. We have some genetics studies involving several institutes. COVID has been a use case for federated learning pretty much from the start of the pandemic. Also chemical applications of interest. So you can actually expand this for federated learning. It has also a lot of use cases in the mobile phone sector, right, on edge devices, where you want to train more robust models by taking information of millions of mobile phone users into account, for example. And just to highlight, this is a study that we did in our team together with the MGH, Massachusetts General Hospital in Boston, and actually 20 other hospital sites across the globe to train a COVID classification model that predicts the need for oxygen treatment if a patient arrives in the emergency department using federated learning. So that was a nice study that was published in Nature Medicine last year, showing that we can actually do this in the real world. And maybe some historical perspective, right? The real tool that enabled us to do this was the library that we internally developed within what we call the Clara Train SDK, which is a Dockerized solution that provides you with tools for AI model training in medical imaging. We factored out this library for doing federated learning for medical imaging, and that's what we call the NVIDIA Flare now, which has been open sourced recently under Apache 2 license. So this is a community-driven project. Please, have a look at the GitHub if you're interested, and you can file issues, you can do pull requests and so on. We're really looking for active engagement. And so from our experience, right, we already implemented several different ways of doing federated learning. There are different algorithmic variations. There are security protocols that you can employ, like homomorphic encryption, for differential privacy to make sure that there's no data leakage during the training. And the whole thing is API driven, so you can easily extend it for different applications. Some of the key design principles, we're kind of trying to make this friendly to researchers so they can easily experiment, both in simulated environments. You know, in a lot of cases, you just want to try out different algorithms on some kind of random data splits of some data that you have to simulate the federated learning scenario. Or you can then easily transfer that into a real world and set up a collaboration between several hospitals or several entities and train your models. So that's where we want this to be applicable for real world scenarios, having the security and privacy in mind, and also system failures. We need to be responsive to communication errors and things like that. So maybe this is summarizing again what I said, kind of privacy preserving algorithms. We have reusable components like different training and evaluation workflows. It can be extended. One big point is actually that it's the federated learning framework itself is agnostic to the data science library or machine learning library you want to use. So we typically have examples in the deep learning world, so using PyTorch or TensorFlow, but it could be all kinds of computation that you want to run in a distributed fashion, right? So we also have examples that just use NumPy to compute some statistics on the client's data and share some aggregate histograms and things like that. Yeah, on the algorithms side, we have currently this set of examples. The vanilla approach, which is a really good baseline to do federated learning, is called Federated Averaging. Has been proposed in 2017, I think. So it's still relatively new, but as I said, there have been many real world studies now. But that allows you to basically train models independently on each side, on each institute. You send updates to a centralized server. The server aggregates the model updates, sends back an updated model, and the training continues. And if you iterate that many times, then you see the models converging. But there is this challenge of data heterogeneity, right? You could have clients that have very different distributions of how their data looks like. So you have the risk that your models start converging from the global model. So there are techniques like Fed proxy, which are trying to penalize this divergence from the global model to help with the training. Or we have adaptive federated optimization, which uses more complex optimizers on the server side to update the global model rather than just doing like an averaging of the updates. And we have, there are alternative ways of doing the sending of the model updates across different sites, right? You can also do this in a circular fashion. So we have something called a cyclic weight transfer, where you train on one side, you pass it on to the next side, and so on. Sometimes helps also with the data heterogeneity problem. There are other popular algorithms that we implemented, like scaffold, that applies correction terms during the training to achieve a better model convergence. There are approaches for handling fairness and personalization, right? As you can imagine, you can train joint models, but each client could also have models that are optimized for their local data distributions. So we have something called DITO, which is kind of the state-of-the-art algorithm for doing the personalization of the federated learning. And all of these can be extended by using our differential privacy components and homomorphic encryption, for example, to ensure that anything you send to the server is actually encrypted, and then therefore it's much less likely to leak any information. Yeah, so with NVflare, you can basically handle the entire development process, right? In a federated learning setting. So first we need to provision and authenticate the different players in the federated learning scheme, right? You have different clients, you have a server, we have administrators that can run different experiments, can define the configurations for the different experiments that you want to run. So those all need to be securely authenticated, and we need to make sure that only entities that agree to join this federation also can join it and communicate with the central server. So we're using SSL authentication for doing this. We have workflows that can do data analysis first to allow the data scientist actually running the experiments to get a picture of how the data looks like. Is everything, all the pre-processing done correctly? You can basically deploy these pre-processing workflows as part of your NVIDIA Flare run. Sorry, I didn't introduce this concept, but we basically have a concept of a run, right? That's executing a certain workflow across the federation. There are different workflows that can be run to train the models. And as I said, we can allow different collaborators on the edge, so on the clients, to use the different favorite training library to allow different data science workflows. And at all of this, we also have monitoring solutions like auxiliary communication channels that allow you to do things like streaming of TensorBoard values during training, right? Every client doesn't have to constantly send updates, but they train for a certain amount of time on their local data. But while they're doing the training, you might be sending additional information like TensorBoard values, and you can monitor them in a central place.
Holger, but before you move on, should we answer a few questions?
Oh, sorry, I don't see the chat here, but
yeah,
sure.
Yeah,
maybe if you can highlight questions.
Yeah, there's go first. A question, very simple, a quick question one. Are these slides available later on?
I think yeah, sure. We can make them available.
Okay. Oh, another quick question is, can you run R code in this framework?
Yeah, it's R. Okay. That's a good question. We are a Python-based framework, so there needs to be some sort of wrappers that allow you to execute an R code. But I think it's in principle it's possible.
Okay. So the other questions that actually I think Andy already answered, but I want to just for the benefit of other people. So so basically, somebody's asking, so how do you compare OpenFL versus Flare? OpenFL, of course, that come from Intel as open source, the Federated Learning framework. So I think Andy already answered, but maybe you can tackle it as well.
What did Andy say?
Well,
yeah,
yeah.
I'm not working.
Andy, you can directly unmute yourself and talk about it.
Yeah, I think this is Andy here. I think there are the multiple open source libraries for federated learning, as OpenFL is one of those. I think they're the other ones. And we not really try to compare, all the different solutions that likely have different benefits. the NVflare, I think what we try to do here is, we try to make both the academic research and the real world federated learning possible. I mean, it's reflected a lot of learnings we have had in the last several years. I would encourage you, you compare with them by yourself, and it's I would like not to make a subjective statement between the OpenFL.
Okay.
Yeah.
Go ahead.
Yeah, I mean, I would say Andy summarized it very well. I see there's also a question regarding the homomorphic encryption.
Yes.
And I think this is like it's an interesting topic, right? The homomorphic encryption does require further larger compute requirements, but it makes your whole system more secure. So in our largest real world study, we haven't used it. Just to tell you kind of what we did practically. But I think as people get more and more aware of potential data leakage risks in federated learning, the use of cryptographic techniques will become more and more important. So we already have the solution there, and it's we tried it in real world scenarios on our internal data, and it's working in a reasonable amount of time. So it's definitely feasible to run nowadays. I would say like a few years ago, that wasn't true. Like there were no homomorphic encryption solutions out there that could even run in a reasonable amount of time for these kind of tasks. But for the model sizes that we work with, like standard deep learning models, and the kind of communication frequency that you typically need to run the federated learning, it's definitely feasible to run it all using the homomorphic encryption solution we have in NVFlare. Okay.
I think that's all the questions, so you can continue.
Exactly. So yeah, just to talk about the high-level architecture of NVFlare. So I talked about these different steps, right, that you need to do for the end-to-end workflow for federated learning workflow. So the first thing is the provisioning. So we have APIs there that allows you to build startup kits, as we call them, that then can be used to start up the server. It could be running on AWS or on some institute server or any cloud provider you want to use. And then each client has their own startup kits to then securely connect to that server instance. And we have startup kits for the administrator. So this is typically the data scientist who is setting configurations for like how should the experiment be run. Of course, there's some sort of access control of what kind of algorithms the administrator can run. Depending on how. Of course, there's always some form of trust that is needed to be established between members of this collaboration. So typically, there is also a phase where you sign some sort of agreement between participating sites, especially in healthcare applications. Typically, each institute, they know each other, they want to work together. So in this scenario, it's a little bit different to maybe some of the mobile phone applications where you don't know the clients, right? It's just some random Google user who's sending updates. Could be anything. But here in our use cases, we typically have this trusted scenario where we know each other, and the administrator is typically somebody who is assigned to run the experiments, right? And everyone agrees that this person should be running experiments. On the communication side, for the federated learning, we use gRPC because there are larger data quantities that need to be transferred, right? The model updates. And for the admin communication with the server, we use TCP. All of these access points for the different components are designed with an API, so you can always extend it or change it for your custom use cases. Yeah, this is kind of summarizing what I just said, right? We have the open provisioning API, we have the server controller API, the client worker API, and the admin API. The admin API is something that I use a lot as a data scientist developing, FL experiments or setting up new use cases. It allows you to run the whole system kind of in an automated, scripted way. But I should mention that we also have this admin console. I think I have a slide later that allows you to interactively interact with the federated learning system to run new experiments, to look at results and things like that. Maybe one of the major concepts that we have is the controller and worker API. So that is really what allows you to do general this decentralized compute. But the server implements the controller workflow and is basically assigning tasks to each client. So in the federated learning, this would be the learning task, like local training. The client, once it receives the task, is executing it, is sending back results. In the federated averaging scenario, it's the model updates that are being sent back. Then the controller is calling some aggregator functions that actually summarizes or aggregates or does like a weighted summation of all the updates from all clients, and sends back the global model for the next round of training. So the next round will be a new task for the clients. So, but you can see from this API design, right, that the task can be anything. You can always implement some form of computation that needs to be executed on the client and some results that are being sent back. And the controller is somehow processing the results and does define a new task or continues the same task in a loop. So it's very, very flexible design. At the same time, we can also apply additional filters for each task when on both the client side, on the server side, when the client when they are sending or receiving information. So one example of that is, for example, the differential privacy protocols that we sometimes apply to updates that are sent to the server. So that means like you're adding some noise to the updates in order to obfuscate any information that might be in the updates and could reveal personalized information. Or another example is the homomorphic encryption, where you actually apply an encryption here on the client, and so the server only sees the encrypted values. And actually, with homomorphic encryption, it allows you to do an addition in the encrypted space and send back the encrypted value. So then the client only decrypts this message and continues the training. And that way, the server never sees raw information about the model updates during the training. Yeah, so the most common federated learning workflow, as I said, is the federated averaging, and that's typically implemented in a scatter-gather approach, where the current global model is sent out to all clients, and then it's waiting for a certain number of clients to come back. So to then do the averaging and update the global model and redistribute it to all clients. So that's our typical workflow for Fed averaging, Fed opt, Fed prox. I guess most of the federated learning algorithms, at least in horizontal federated learning, are a variation of federated averaging. Then we have other workflows like useful for evaluation. So after you train the model, you can actually evaluate the model. It could be just a global model that's being evaluated on each side, or we have a scenario where in the personalized federated learning example, where each side also has their locally optimal model, we can exchange those models with all the other sides to evaluate them and then get information about the robustness and generalizability of all these models. So in that way, you can get a very kind of complex or a very informative matrix, right, with different validation metrics that show you the global models. So these are the models that are saved on the server. Typically we have like the final model, just the last model after training, or we do like a model selection process that is based on validation scores that each client is computing, or we have all the best models from each side, right? And then you have this kind of matrix that shows you how the model performs on each testing data on the other sides. This is the admin console for this interactive control of the federation that I talked about earlier. And we also have the API that can allow you to do automated scripting of all the commands that are available here. But you can see hopefully that there are commands like uploading an app. So here the app is a set of configuration files that define things like what workflow to use, what training configurations, and so on. You upload that to the server and you can deploy it to each of the clients, and you start the app. So in that way, that's typically what we define as a run, federated learning run. And as I said, this app could be containing anything. Could be the federated averaging workflow, could be evaluation workflow, could be something else. This is for automating this admin console. So you have it's a Python-based API that allows you to kind of script these commands and do it in an automated way. And then here we have a list of our examples that are currently in the repo. If you want to get started, maybe for deep learning focus, the Hello PyTorch example is the best starting point. Shows you like how you implement a client executor on the client side that implements, PyTorch training loop basically, and on the server, you use the standard scatter and gather workflow to do the federated averaging. Yeah, so we have several end-to-end examples that go through different variations of how you can do federated learning. Federated averaging is maybe on Cipher 10 is a good starting point as well. And also here we're using the admin API to run different configurations, different algorithms in simulation. And that allows the researcher to quickly try out different configurations. You can plot comparisons of different runs, compare different algorithms to each other. And here's an example of this cross-site validation, as we call it, where the best model on each client is being exchanged with the other clients to tell us about the generalizability of the model. And that can be actually, this is a real study that we did for breast mammography, breast density classification, actually. And in that setting, we actually also looked at how powerful a model could each side or each hospital train on their own, right? So there's a left-hand side, what we call local, and then how generalizable are these models. You can can typically see that these models work well on their own data, so that's the diagonal, but they really don't work really well on the off diagonal. While when you train in federated learning setting, you get models that are working even better on their own data, and they're more robust on the off diagonal, right, on the other side's test data. I mean, here in this application, there's still a gap, mainly because of this big data heterogeneity you can get in breast mammography images. It really is dependent on the patient population and the scanner equipment that each hospital has, but it's definitely better than any of the sites could be training on their own. Here we have an example of the federated analysis, as we call it, where you don't do training, but you just compute some statistics on each side and like the image intensity histograms, right, of the entire data set. So it's unlikely that these histograms are leaking any patient identifiable information. So we have a threshold here that we're only sending histograms of at least 10 images to make sure that enough information from different patients was averaged so that no leakage is happening. And then the workflow can actually take those histograms and also compute a global histogram. This can be very useful to figure out how much diversity there is in the data, what kind of algorithm I should use for federated learning. Maybe there needs to be some specific regularization in order to compensate for diversity in the data, or some special weighting or between different clients needs to be applied to compensate for differences. So this can also be achieved with NVflare. And here, this is just showing some things that we already talked about. A homomorphic encryption is a way of using cryptography to do the aggregation on the server without ever revealing the raw floating point numbers that are being sent to the server, right, in form of model updates. So here, each client is encrypting their update messages, sends it to the server. The server has no decryption key, so it just does a computation in encrypted space. It sends back the result, and then the clients decrypt it, and they get the same as if the addition would happen in the raw space. And the other approach is differential privacy, or it can be actually combined, right? Differential privacy is at this Gaussian noise or some form of noise that is being added during the model training, or at least to messages that are being sent to the server to ensure that no individual information is being leaked. Okay, so this is, I think, my final slide. I actually wanted to highlight you that we have an upcoming NVflayer Developer Day at GDC on March 21st. It's free registration, so yeah, please. Like once I share the slides, this should be a link for you to click on. But this is going to be a interactive session where you can really deep dive into NVflayer development. Okay, thank you. If there are more questions, let me know.
Yeah, there's a few more questions. Let me pick up the last one first. So how do you see the future of the federated analytics? So what are the use cases for federated analytics?
Yeah, I think this is a very broad topic, right? I think this is really the direction I want to the field. I want to see the field moving. Doing any kind of data science in a federated setting. But as a scientist myself, I don't care about individual data points necessarily, but I want to gain knowledge from large data sets. And they can be, I don't necessarily need to have access to all the data in a centralized place, right? I want to have a way of running analysis or analytics, as you say, in this distributed infrastructure to gain the knowledge. And I think that's something we're working towards, right? We want to go past just AI model training, but maybe doing statistics in the decentralized way. We can learn all kinds of machine learning models that also inform you, right? Decision trees can be learned in a decentralized way. So yeah, I think there's a big bright future for federated analytics.
Yeah. Okay. The other question is when you're showing the examples on the GitHub, and the question is there a CNN examples?
Yeah. So the Cipher 10 is CNN, for example. It's kind of a good starting point. I think most of the all of the PyTorch examples that we have are using CNNs.
Okay, the other questions I think Andy already answered. Basically, David from Germany said it's has some issues installing NVFlare in the company. Try to see whether he can make it easier to install like a Flower. And Andy asked him to fire issues, and probably we can just address it. So, any other questions people has just asking? We have Holger and Andy both here, so. Talk about the federated learning in general. So,
yeah, in general, I would just encourage everyone to file issues in the repo. Like our researcher and engineering team are both actively engaging with users, and external contributors to this library. So there's also a discussion forum where you can ask all kinds of questions. So please, interact with us if there's any question.
Okay, so another question: do you see homomorphic encryption as superior to secure multi-party computation in terms of computation overheads?
So the main reason why we started with the homomorphic encryption is that it requires less communication compared to the secure multi-party computation solutions. So in that, from our experience, this was the main issue we had, like in real world applications of federated learning, that some clients would maybe not come back with their model update. So in that case, you cannot do the secure multi-party computation. While for the homomorphic encryption, you can actually still do the averaging on the subset of clients that send you an update, right? So in that way, it's more robust. But there are certainly use cases where you could see maybe there's a benefit for secure multi-party computation.
Any other questions? I probably ask one, but I saw Google recently published their federated learning in production, mostly for Android, using LP type of applications. Is that the directions are this SDK also moving to as well?
This is a good question for Andy again, if he's on the call. But yeah, I think this is Google is addressing more of the cross-device application, right, where you have some tens of thousands, millions of edge devices, and they have small amounts of data. They're sending back some updates. Like at least historically, we have not been focused on that use case. We are more focused on the so-called data silo scenario, where each client is a hospital. They have like large compute, GPUs, and typically large amount of data. So we are talking about like a few dozen or hundreds of clients that are talking to the server. So I mean, this is our use case so far, but I think in general, the cross device is also very, very interesting.
Good. Anybody has any other questions? This is a new area. I mean, a lot of people, a lot of companies working on this. As you see here, NVIDIA is working on that, and Intel is working on that. Google is working on that, and there's just a name a few, and there's a lot of. It's a brand new frontier, I think. So NVIDIA has done a lot of work already. So anybody that's working in this area, I mean.
Yeah, there's probably also a lot of need for standardization, right? Like these potentially these different frameworks can talk to each other at some point. So you don't have to install NVflare on your client if you already have some other solution installed, right? But you want to join a federated learning consortium collaboration in some form. So I just would like to mention that we also, at least, I don't know if there are many people on the call who work on medical imaging or healthcare, but there's a forum or community effort in medical imaging called MONAI, which tries to standardize some of the common concepts for doing deep learning with medical imaging. And there we also have a federated learning working group that is interested in standardization aspects of federated learning. So yeah, please engage if you're interested.
Okay, so there's another question coming out from Nashi Shaha. I hope I pronounced it right. He said, would any of the attendees to be willing to connect with him to discuss the federal learning? If so, please contact with me. Okay, so you can contact. Could I run examples in Google Colab environment first? How do I find notes and hints? I guess it's talking about in the Colab or notebook type of things. Can you use the SDK to run it?
It's just a pip install that you need to run. I think you can just run it in Colab. It's we distribute the SDK as a pip package, so you should be able to just pip install and then run any of the examples.
Yeah, one thing as you may want to make sure, so NVflare does not require using GPU. Okay, if you just want to run on CPU, we have no dependency on the GPU itself for the NVflare. Even so, we will encourage you use the GPU for the model training, all those stuff, but it has not a requirement.
Okay. All right, I think that's all the questions. Oh, so somebody is saying that.
Okay. Yeah.
Colab provides a GPU. Colab. Okay. Okay. Colab has GPUs. Okay.
That's a good thing. Yeah.
Okay. All right. I think that's all the questions we have, and we want to thank you, Holger and also Andy, for answering the questions and give us the presentation on the NVflare. So the slides will be, after the words, and I'll ask for the slides link and I'll post it. And then also I will share the recording probably a day or two in the meetup page. Thank you all. I'll see you, hopefully see you next week.
Thank you.
Bye. Thank you. Bye.